have you ever looked at, say, a robot or a smart lamp and wondered, how does that tiny little computer chip inside actually make something big happen in the real world? Well, that's exactly the magic we're going to dive into today. We're bridging the gap between the low-power world of digital brains and the high-power physical world. All right, let's say you've got this amazing idea for a new project. Maybe it's a custom robot or a cool smart home gadget. Whatever it is, you know it's going to need a brain to run the show, right? And that's where our friend the microcontroller comes in.
So yeah, this microcontroller, it's the brains of the whole operation. It's super smart, it's fast, but you know, it's got a secret. A pretty big one, actually. A major limitation that we have to deal with. And here it is. The big secret is 20 milliamps. That's it. That is the absolute maximum amount of current a typical microcontroller pin can safely push out. Now that's just enough to light up a tiny little LED, but if you try to power something like a motor with that, oh, you're going to have a bad time. You'll fry that chip, guaranteed. It's kind of like trying to tow a truck with a piece of string. It's just not going to happen.
So that's the core of our problem, isn't it? We've got this brilliant, intelligent brain, but it has absolutely no muscle. So the big question is, how do we give it the strength it needs to actually interact with and control the real world?
What we need is some kind of middleman, an interpreter, right? Something that can take that tiny, weak signal, that faint whisper, from our microcontroller and turn it into a powerful command, a mighty roar. And in the world of electronics, we've got just the thing for that. We call it a switch. Okay, so it's time to meet the muscle. Let's get introduced to the components that are actually going to take those orders from our brainy little microcontroller and do all the heavy lifting for us.
So we've got two main players in this game. First up is the BJT, the bipolar junction transistor. Now think of this one like a faucet. A tiny little trickle of current from your microcontroller is like a gentle turn of the handle, and that opens up the main valve, letting a much larger flow of current gush through. Then you've got the FET, or the field effect transistor. This one's a bit different. It acts more like a modern light switch. It just needs a little bit of voltage from the microcontroller to flick it on, and bam, a huge current can flow. The cool thing is, it takes almost no energy to keep that switch flipped.
Okay, so check this out. This is the classic recipe for using a BJT as a switch. You've got your signal from the microcontroller coming in. You've got the device you actually want to power, and the transistor, it just sits right in the middle, ready to make that connection and get things moving. So, how does this whole thing actually work? Let's break it down. That tiny little signal from your microcontroller, just a few milliamps, goes to the base of the transistor. Think of it like a key in a lock. Once that key is turned, it unlocks a much larger path for current to flow. We're talking up to 100 times more. This bigger current flows from the collector to the emitter. And because your high-powered device is connected to that path, voila, it turns on. Simple as that. All right, so now that we've got the hang of the basic electronic switch, let's level up a bit. We're going to look at some more specialized tools for controlling all sorts of different devices you might have in your projects. Let me introduce you to the relay. You can think of this thing as a heavy-duty, old-school bodyguard for your microcontroller. Here's how it works. Your microcontroller sends a small current to a little coil of wire. This energizes the coil, turning it into a magnet, and that magnetic field physically pulls a lever to close a completely separate, high-power switch. It's pretty cool, right? It's literally like having a tiny robot butler do the dangerous heavy lifting for you. So what's the big deal with relays? Well, their number one advantage is that total electrical isolation. It builds a complete wall between your sensitive microcontroller and the high-powered load. Total safety. Plus, they can switch both AC and DC, which is super flexible. But there are downsides. Because they have actual moving parts, they're slow. They can also wear out over time, and all that sparking isn't great. And that coil? It actually takes a decent amount of power to keep it energized. So relays are awesome for certain things, but they're definitely not the answer for everything.
Okay, so we know relays can handle the big stuff, like the AC power coming straight from your wall outlet. But let's be honest, they're kinda clunky and slow. So that begs the question, is there a better, more modern, solid-state way to control AC devices?
And the answer is yes. Enter the triac. This thing is purpose-built for AC. See, a regular transistor is like a one-way street for current. That's perfectly fine for DC, which only flows in one direction. But AC power, the stuff from your wall, it alternates, flowing back and forth. A triac is basically like a smart two-way street. It's built from two devices called thyristors, which are kind of like one-way gates, but they're put together back to back. This setup allows your microcontroller to control the flow of current in both directions of that AC cycle.
Alright, so we figured out how to turn things on and off. That's huge. But now, let's get to the really fun part, making things move. This is where things get dynamic. Welcome to the challenge of motion.
At the very heart of most motion projects is the simple DC motor. It's a beautiful concept, really. You send an electrical current through it, and it creates a rotational force. It spins. It's that simple. So our job is just to figure out how to precisely control that current, because if we control the current, we control the motion.
When it comes to motor control, we usually break the problem down into three main challenges. First up, speed control. The key tool here is something called PWM, or pulse width modulation. It's a super clever trick where you're just turning the power on and off really fast, thousands of times a second. By changing the ratio of on time to off time, you control the motor's speed. Pretty neat, huh? Then there's position control. What if you need to move to a very specific angle? That's where you'd use a servo motor. And finally, for super precise incremental movements, like in a 3D printer, you turn to a stepper motor.
Now, you could try to build all the transistor circuits to handle this stuff yourself, but honestly, why reinvent the wheel? There are amazing specialized chips out there called motor drivers. You've probably heard of an H-bridge. These things are designed to do all the heavy lifting for you. All your microcontroller has to do is send high-level commands like go forward or set speed to 50%. The driver chip takes care of all the complex, high-current switching needed to make that happen.
So there you go. That's your power control toolkit in a nutshell. You've got the transistors, the relays, the triacs, the motor drivers. You now have the fundamental knowledge you need to command the physical world with just a few lines of code.
And this is probably the most important takeaway from all of this. You've got to choose the right tool for the job. So let's recap. If you're doing simple, fast, low-power DC switching, like for LEDs, a transistor is perfect. If you need to switch some really high-power stuff, either AC or DC, and you want that electrical isolation, a relay is your friend. Need to control an AC load like a lamp or an AC motor? Go for a triac. And finally, for any kind of precise control over a motor's speed and direction, a dedicated motor driver IC is absolutely the way to go.
And here's a look at how it all comes together in a real circuit. You can see how all these different components work together. You've got your microcontroller, the brain, sending out its low-power logic signals. Those signals go to the driver chips, the muscle, and they handle the high-power switching to control things like motors, lights, and sounds. It really is like a symphony of electronics, and the cool part is, you now know how to be the conductor.
So, you now have the tools. You understand the core concepts needed to bridge that critical gap between the digital world of your code and the physical world of action. You can make things happen. The only question left is, what are you going to build first?